Turn off the camera for the broadband. So, any question, Agnes?
No, I don't have any.
You don't have any? Okay, great. So I'm going to start to share my screen. And I think I'm sharing.
Yes, you are.
Thank you. Okay, so we are in the new topic. And this is the topic, as you can remember, optimization in, no, this is not the topic. Yeah, this is the topic, sorry. Is it? Oh, no, we are going to start a new topic, actually. Yeah, so we are going to start existence of solutions, basically the Weierstrass theorem. So that's why I haven't included the new picture. So let me open the syllabus for your convenience. By the way, maybe you can see this is our Moodle page, and I included this link. It's a dictionary of mathematics to translate between English and Estonian, so it may be convenient for you, just in case. And this is our syllabus. So we are right now in existence of solutions. And it says here 3 weeks. It's not 3 weeks, it's just one. So I made a mistake, I apologize. And the objective is, at the end of this topic, the students will be able to use a Weierstrass theorem to establish the existence of solutions of some optimization problems. And this is what we're going to cover. So we're going to introduce the Weierstrass theorem with some concepts from mathematics, especially compactness. The Weierstrass theorem in applications, and finally, next time we're going to give a proof of the Weierstrass theorem. Okay, so this is what we intend to cover, and also I would like to call your attention to the fact that there is already some homework assigned in the Moodle page. So it's this homework which is due October the 9th. Okay. So I'm referring to section 2.6, and I'm asking you kindly to try to solve the problems for that section. The due date is October the 8th, actually, it says here, but I'm going to leave this activity open till October the 9th for your convenience. Okay. Also, there is some assignment number 2 and assignment number 3, but don't take care of them right now. Any questions?
No.
No. Okay. So let's start the lecture. So we are in the new topic, and this topic is existence of solutions. More precisely, we're going to be talking about the Weierstrass theorem. Okay, Weierstrass theorem is the most important tool that we have to prove the existence of solutions for maximization and minimization problems. And we are going to introduce it today. But before that, a motivation. So I'm going to start with a remark. And I would like to remind you that we want to solve the following problems. So maximization problems of some function f of x when x is in D, or minimization problems of the function f of x when x is in D. So those are the types of problems that we are interested in. And the functions are going to be functions whose domain is in Rn, and the codomain is in R. So there are various interesting questions that we would like to solve in this section and in the next sections how to find out if these two problems, have solutions. So in other words, do these problems have solution? How to find the solution? So once you have determined that there is a solution for these problems, you'd like to know how to obtain the solution. More concretely, so we are in mathematics, so we want to find out if there's a chance, are there tools mathematical tools to find out if there is a solution? Okay, which conditions on D guarantee that there is a solution? So under which conditions can we guarantee that these problems have a solution? And likewise, you see, we have a set D, but we also have a function f. So the question is, which conditions on f guarantee a solution? And of course, we are in mathematics and we would like to be as broad as possible. So in other words, the results that we obtain, we want to be as general as possible. So these are just some questions that motivate this section and the subsequent sections. I'm going to mention that next. So the road work, the road work, the path for this week is the following. So we are going to state Weierstrass theorem. We're going to provide applications. And we are going to prove this theorem. Okay, maybe you already studied Weierstrass theorem. Maybe you already proved it. But I would like to check the proof, especially because, you know, there are some concepts from topology which I would like to use throughout the course, and that's why I would like to make sure that we understand the concepts and we talk about the same concepts in English. Okay, so this is what we're going to do. I don't know if it's clear, ladies.
Yeah, it is.
Okay, great, thank you. Okay, so I'm going to start with a definition. Okay, so I'm going to consider with a collection of subsets of Rn. This P that I'm using is for the power set of Rn. And we have a collection of subset of Rn. I'm also going to fix a subset of Rn. For concreteness, we can think of U as a collection which is indexed by alphas, U alpha, such that alpha is in omega. Okay. We say that U is a covering of the set A if the following happens. Okay, so I'm going to wait for you a second to copy. Please let me know when you finish.
I'm done.
You're done? Okay. And Hilary and Eva, everything, you're with me?
We are also ready.
Okay. Okay, so again, I'm going to change the page, but before that, let me read it. So suppose that you have a collection of subsets of Rn and a subset of Rn. We say that U is a covering of the set A in the case that the following two conditions happen. So first condition is every U in this collection is open. And the second property is that A is a subset of this union. So the union of all sets U alpha. So in other words, I'm taking the union over all the sets which are in this collection, right? So this is a covering. So basically it's a collection of sets of open sets which covers the set A, this set. And I'm going to define now what a finite subcovering is.
Sorry, we don't understand what's the second condition, like the last part.
Okay, so this is another way to represent it. So never mind it. So I was trying to be, try to make it more understandable, but maybe in this way it's simpler. So what you're doing is just taking the union of all of these U alphas. Okay. So we are requiring for A to be a subset of the union of all U alphas. That's it. Okay. I don't know if that is easier.
Yes, thank you.
Oh, you're welcome. Okay, let's define what a finite subcovering is. So to that end, I'm going to take a covering. So let U be a covering for the set A. Okay, so then this collection, U prime, which consists of finitely many sets in U, is a finite subcovering if A is still a subset of this union, this finite union. Any questions?
No.
No? Very well. So a finite definition, final definition. So let A be a subset of Rn. Then we say that A is compact if given any covering of A then you can find a finite subcovering. Okay, compactness. The concept I'm defining in this here, it's a topological definition. Now, before I move on, I'd like to ask you if you have seen compactness before in any of your courses.
Me and Hilary have, because we took topology last year, and also I think last year in your course we also looked at this definition and also the Weierstrass theorem proof.
Okay. Okay, great. So, but how about in a vector calculus? Did you study compactness or not?
We don't recall it.
Okay. Okay. So I'm just going to mention some few properties about compactness and some examples before that. So, for instance, if you consider R is not compact. And it's not compact because this definition is not satisfied. So there is a covering of R which has no finite subcovering. And I'm going to show you one of them. Yeah. So consider this collection. U is a collection of sets of the form, intervals of the form -n to n. With n in the naturals. It's easy to see that U is a covering of R. But unfortunately, it does not have a finite subcovering. So there doesn't exist finite subcovering. And I don't know if this is understandable. Could you follow me here?
Yes.
Good. Thank you. Thank you, Agnes. Okay, another example, which is also simple. is the following one, Rn, for instance, is not compact either. So again, you can consider the following covering. So it's good, the collection of all the, what I'm going to call balls with center at 0 and radius n. For n in the naturals. And here the balls, what I'm calling a ball, is the collection of all x in Rn with the property that the norm is less than n. Again, so this is a covering, but there is no finite subcovering. And therefore, Rn is not compact. Okay. Okay, another example. Can we turn the page over?
Yes, we can.
Okay, thank you.
I have a question.
Yes.
Student naturals are like a compact set or not? Natural
Oh, that's a
numbers.
good question. That's a good question. So let's give another example. The naturals are not compact. Okay, why is that? Well, you can provide some covering. Let's say consider these sets n minus 1/2, n plus 1/2, such that n is in the naturals. Okay, again, this is a covering. It's obvious that it's a covering. So let me make them bigger. So this is 0, 1, 2, I'm sorry, yeah, 1, 2, 3, so on. And these intervals go from n minus 1/2 to n plus 1/2. So this is one of the intervals, then this is the other interval. So only one natural number is within each of these intervals. So in this case, there is no finite subcovering. Why is that? Because if you take a finitely many of these sets, only finitely many natural numbers are going to be covered. Not all of them. So yeah, the naturals are not compact. Yeah, good question. Another example. For instance, we can consider the collection of real numbers of the form 1 over n with n in the naturals again. And you can see that A is not compact. However, if you consider the same set, union 0, then this set is compact. Intuitively, is this true? What do you say, ladies?
No, I don't understand it right now.
Okay, so I'm saying that A is compact. A is this collection. So let me try to make a picture here. Let's first get a picture of this this set. So let's say this is 1/1. Then you have 1/2, which is 1/2. 1/3, which is 1/3. 1/4. Okay, all of these points are going to form the set A, right? And they're going to pile up closer and closer. Okay. But then you're also including 0. Okay, so this is 1/4. I'm saying it's compact because, okay, suppose that you take any covering. So any covering of this set, so it's going to cover all of these points. So maybe those are the sets, so on. But 0 is going to be in one of the sets of the covering. So there is an open set in which 0 is there. But not only 0, infinitely many points are going to be in this set, in this green set. Outside, there will be only finitely many. And each of them is going to be covered in one set. So at the end, you can choose finitely many sets in any covering. To form a subcovering. And that's why A is compact. I don't know if you're at least intuitively convinced about this argument.
Yes, thank you.
Oh, you're welcome. That was Eva?
Yes, but Hilary asked a great question.
Okay. Oh, okay. I was confused. Okay, thanks for clarifying. Okay, another example. For instance, if A is a finite set, then A is compact. So if there are only finitely many points in A, then A is compact. Okay, and that's in general. Another example. So if the set A is the interval 0, 1, open on one side and closed on the other, for instance, then A is not compact. So we have to find a covering which doesn't have a finite subcovering. There are many, but I can propose this one. How about the collection of intervals that go from 1 over n to 2? Okay, notice that this is a covering of A, and it doesn't have a finite subcovering. Okay, and we can stay here and talk about more examples. But what I would like to do is to remember some of the properties of compact sets instead. And that's what I'm going to do in the following remark. Okay, do we change the page, ladies?
I'm ready.
Okay. Let's change the page. So we have the following properties. First one, if, for instance, you have C1, C2, a finite number of subsets of Rn, which are compact. Well, it turns out that the union of all of them is compact. So finite unions of compact sets are again compact. The empty set is compact. And in Rn, compact sets are completely characterized. More precisely, a subset of Rn is compact if and only if C is closed and bounded. Okay, so this characterization is pretty good because it tells us exactly which are the compact sets. For a set to be compact, it has to be closed and it has to be bounded. And we know what closed is. So closed is the complement, a set is closed if its complement is open. What's the meaning of boundedness? So we recall here the definition of bounded. So recall that C is bounded if there is some R greater than 0 with the property that C is contained in the ball. Let me write it down. C is a subset of the ball with center at the origin and radius R. So this is the meaning of boundedness. maybe we should recall what the ball with center at the origin and radius r is. So that's the collection of all the vectors whose norm is less than r. Okay, so and this is something that happens exclusively in Rn. So we would like to say, for instance, that this characterization also happens for metric spaces, but that's not the case. So again, so this is for Rn. So in Rn, a set is compact if and only if it's closed and bounded. Okay. Okay, more properties. So suppose that a function f from Rn into Rm so this is M, is continuous. If A, okay, I'm sorry. If this happens and A is compact, then its image is also compact. So the image of a compact set under a continuous function is compact. And probably if you have taken topology, you have seen that this theorem is satisfied for topological spaces in general. Another property is the following. So if A and B in R are compact, then the Cartesian product, which is going to be in R2, is also compact. So the Cartesian product of compact sets is again compact. And then you can use induction, right? I mean, I'm not going to write it down here, but if you have that A1, so on, AN are compact, then the Cartesian product of all of them is also going to be compact. So the Cartesian product of finitely many compact sets is again compact. Okay. And of course, I mean, naturally, we would like to know if, for instance, if you have A alpha, which are compact for every alpha in omega, the Cartesian product of all of them is compact. This is true. Okay, provided that this Cartesian product has the product topology. That's in case that you have taken topology. This is a theorem which is called Tikhonov's theorem. And it's a consequence of Zorn's lemma, but we're not talking about topology, right? So, but that's a natural question in mathematics, okay? But for our applications, this is going to be enough. So the Cartesian product of two compact sets is compact. And finally, one last property is what we call the Heine-Borel theorem. which states the following, that A comma B, closed A comma B, is actually compact. Okay, those are just some properties of compactness in the in Rn. I hope this helps to remember the properties and the definitions. We are going to use some of them in the following. So if you have any question, please let me know now.
No.
No? Okay, thank you, Agnes. Okay, there is one theorem that provides more characterizations on compactness and states the following. Let A be a subset of Rn. Then the following are equivalent. A is compact. Okay, every infinite
What the TFA
means.
Okay, sorry. Yeah. The following are equivalent.
Okay, thank you.
Okay, sorry. Yeah, so this is a convenient way to abbreviate it. So we were saying the following are equivalent statements. So the first one is A is compact. And I'm gonna wait a second for you to finish. Please let me know when you finish.
I'm done.
Thank you. Okay, Hilary and Eva.
We're also done.
Uh-huh.
We are also ready.
Okay, thank you. So, second statement. We were saying, so every infinite subset of A has a limit point. And the last one, which is also a consequence of the axiom of choice, every sequence in A has a convergent subsequence. Okay, this property here is sometimes called the Bolzano-Weierstrass property. that every infinite set has a limit point, right? And this condition is sometimes called sequential compactness. So the theorem tells you the following. So in Rn, a set is compact if and only if satisfies the Bolzano-Weierstrass property, if and only if it's sequentially compact. These are nice characterizations of compactness in Rn. We're going to use them at some point. But what I would like to do is to introduce the Weierstrass theorem. Which says the following. Suppose that D is compact and suppose that the function f goes from D into R is continuous. Well, then there exist vectors A and B in D with the property that for every x in D, the following is satisfied. F of A is less than or equal to f of x, less than or equal to f of B. And I'm going to represent this for a function that goes from R into R. Okay, suppose that this is the interval a comma b, which by the way is compact if it's closed. And this is your function f. I'm sorry, this is unfortunate. Okay, so I'm going to call this interval c comma d. Sorry. And your function here in this case is a function that goes from c comma d into R. And as I mentioned before, you notice that this set is compact. Well, notice that in this case, you can find numbers A and B this will be actually B. And this is actually A. And you notice that indeed f of A is less than or equal to f of x, less than or equal to f of B for every x in the domain. This is the graphical representation of Weierstrass theorem. I'm going to mention something more about it, but I'm going to use the next page, so I'm going to wait for you.
I'm ready.
You're ready. Thank you. And Hilary and Eva, can we move on?
Yes.
Okay, thank you. Okay, next page. So a small remark. On the occasion of Weierstrass theorem, so in other words, if it turns out that the function f is continuous, and d is compact, then it turns out that the function f attains its maximum and its minimum. Okay, so in other words, you see, f of a is going to be the minimum of the function f of x on this set, and f of b is going to be the maximum. And I'm referring to these vectors a and b in the theorem. Okay. What I'm going to do now is to give some counterexamples. Let me go back to the previous page. So you see, there are two essential conditions here in Weierstrass theorem. One is that D is compact, and the other is that F is continuous. If any of these conditions is broken, if it's not satisfied, then it doesn't follow necessarily that there are A and B with these properties. And that's what I'm going to try to exhibit on the next examples. Okay. Let's consider this example is the function that goes from R into R, given by f of x equal to x cubed. You know that this function is continuous. In this case, the domain of the function is equal to the set of real numbers, which is not compact. And you know the graph of x cubed? So you know that in this case, there is no maximum or minimum. So you see, in this case, this hypothesis is satisfied. So the hypothesis on continuity, but the hypothesis on compactness is not satisfied. Okay, because these two hypotheses are not satisfied simultaneously, we cannot guarantee that the conclusion is going to be satisfied. Actually, it's not satisfied. Okay. Another example. Could be, for instance, the following one. So consider the function f that goes from -1, 1 into r. Given by the following rule, f of x is x when x is between -1 and 1. And it's going to be 0 in case that x is equal to ±1. Okay, so you can obtain the graph of this function. Okay, so the graph is going to be something like this, right? Let's see. This is -1. This is 1. And at the end point is equal to 0. So what happens in this case? Okay, I'm going to change the page at your convenience.
You can.
Okay, thank you. Okay, so in this case, the domain is the interval that goes from -1 to 1. And it's closed. So closed and bounded means compact. So this property is satisfied. But if you check the graph of the function, you notice that the function is not continuous. And moreover, in this case, the function doesn't attain its maximum nor its minimum. Again, this illustrates the fact that if you break any of these conditions, the conclusion doesn't need to be true. And one more example. Which shows that sometimes, in spite of the fact that these two conditions are not satisfied, the function f still has a maximum and a minimum. Okay, so let's consider the following function. So the function goes from R into R. And it's going to be defined in the following way. So this is f of x will be equal to 0 if x is a rational number. Rational, I said. I'm sorry. And it's going to be equal to 1 in case that x is irrational. I think sometimes this function is called the Dirichlet function. Okay. Not quite sure about that, but you can investigate it. Well, it turns out that in this case, the domain of the function is R, which is not compact. So the compactness condition is broken. About continuity, the function f is not continuous. In fact, it's discontinuous everywhere. So this condition is not satisfied. However, it turns out that the function f attains its maximum and its minimum. And this is easy to see because you see, f of 0, this is going to be equal to 0. This is going to be the minimum of the function. And for instance, f of square root of 2. Square root of 2 is irrational, so this will be equal to 1, and that's the maximum of the function f of x. So the conclusion is satisfied. All right, any questions?
No.
Thank you. Okay, so we're going to come back to some applications in economics, but before that, I'm going to introduce some notation. So this is my definition. Suppose that you have a vector in Rn. And suppose that we have two real numbers, A and B. Okay. Okay, so we are going to say, okay, there are various definitions here. So the first one is we're going to say that x, this vector is greater than or equal to 0 when all the components are, I'm sorry, greater than or equal to 0, greater than or equal to A. In case that xi is greater than or equal to A for every I from 1 to n. So a vector is greater than a number when all the components are greater than that number, greater than or equal to. Okay. And also you may have the strict inequality. So you're going to say that X is strictly greater than A if all the components are greater than A. Okay. In similar fashion, you say that X is less than or equal to B if all the components are less than or equal to B. And something similar for the strict inequality. And then you have the, the pathological cases, right? What's the meaning of A is less than or equal to X, less than or equal to B? Well, this happens if X is greater or equal to A and less than or equal to B, right? And you can continue with more cases like this one. Okay. Any questions?
No.
No? All right. So let's change the page, if I may.
You can.
Thank you. Thank you. Okay, so some examples. So these are applications of Weierstrass theorem in economics. Okay, so let me see applications actually. So the first one is going to be to the utility maximization problem that we saw some days ago. And I'm going to remember this problem briefly. So this was the problem. It was to maximize some function when the independent variable belongs to some set B, which depends on two parameters. Okay, so let's remember this briefly. So the function u is a utility function. Goes from Rn into R. The parameter I is called the income. P has components P1, P2, so on, Pn. this is a vector in R plus n, and this is what we call the price vector. The vector x has components x1, so on, xn, all of them greater than or equal to 0. And here, remember, xi represents the amount of commodity I. And the feasible region took this form. Is the collection of all vectors, x, in R plus n, for which p times x is less than or equal to I. So for convenience, remember this was the inner product. So this was the problem. And this is the meaning of all the notation. From Weierstrass theorem, if we want to solve that this is solvable, the only thing we need to show is that this set is compact and that this function is continuous, right? With these two conditions, that means that there is a solution for this problem. Okay. So I'm going to mention that. So by Weierstrass theorem, it suffices to show that U is continuous and this set is compact. To show, sorry, that this problem, which I'm going to call star, has a solution. Okay, so there's nothing we can do about this function. So we're going to assume that the function is continuous. So assume U is continuous. But we are going to prove that this set is actually compact. And we're going to do it on the next page. Okay. So whenever you're ready.
Yeah, you can move on.
Okay, thank you.
No, please
Okay.
go back for a bit,
Yes.
a little bit.
Yes. It's okay.
Okay, you can't move on.
Okay. Okay, I can wait.
We are ready now.
Okay, so next page. So what we claim is that this set is bounded. And we are going to show that. So take X, any element here. And remember that this X has components x1, so on, xn. All of them which are greater than or equal to 0. All right. I'm going to do some calculations. Notice. Okay, so any X here in this set satisfies this property. P times X is less than or equal to I. So that comes from the definition of that set. But then you remember that this is the inner product in Rn. So this is the sum for I equal 1 to n of xi times pi. All the summands, all the factors, everything here involved is greater than or equal to 0. So notice that this is greater than or equal to xj times pj, and this is for every j from 1 to n. So this term is less than or equal to I. And prices are positive. So we solve and then you obtain that xj is less than or equal to I over pj. This is j, right? For every j that goes from 1 all the way to n. Which means, look at this, so xj, well, this is going to be less than or equal to the maximum of these numbers, I over pi, for I that goes from 1 all the way to n. This number is what I'm going to call R. This is a fixed number. And you notice that xj is less than or equal to R for every j that goes from 1 all the way to n. And this is boundedness, right? So notice that this in particular implies that the infinity norm of x is less than or equal to R. Okay. So this set is bounded. Right? Because we started off by taking in an arbitrary element in this set, and we have shown that they are uniformly bounded by this bound, by R. Okay. So it's true, this set is bounded, and remember what we'd like to show is, we'd like to prove that it's compact. So we just need to show now that this set is closed. Okay. Now the question is, how can we prove that this set is closed? There are various forms to do that. What I'm going to do in this case is to show that if you have a sequence, let's say this sequence is xk, which is in this set, and this sequence converges, I'm sorry, this is xk, converges to some element, then this element is in this set. That's what I'm gonna do. Okay, so that's the clue. So if I prove that, then I'll prove that this set is closed. Okay. So let xk be a sequence in this set. Okay. For the sake of convenience, remember these are vectors. I'm going to represent the components in this way. So x1k, so on, x and k. Okay. Okay. Since these vectors are in this set, then you have that xk is greater than or equal to 0. And you also have that xk times p is less than or equal to I said. And also for convenience, I'm going to remember what this is. So this is inner product, so the sum of xik multiplied times pi from 1 to n. Okay, and suppose then also, as I said before, suppose that xk converges to some vector x. And I'm going to give a name for the components of x. So that'll be x1 to xn. Okay, so this means that this sequence of vectors converges to this vector, right? And this converges implies that this component is going to converge to this component and so on. So the convergence is going to be component-wise. Okay, I'll mention that on the next page whenever you're ready.
1 second, please.
Yep.
We are.
I'm also ready now.
Okay, thank you. So as I said before, that implies that xik converges to xi. for every component, for every I from 1 to n. Okay, so listen, what I'm going to do is I'm going to use this condition that this sum is less than or equal to I. Okay, for every k. So from to star, I'm sorry, from star, just take the limit. So limit when k goes to infinity. Okay, so remember, so star was sum from I equal 1 to k, xik, pi is less than or equal to I. You take the limit. So only this factor depends on k. So you can switch the summation and the limit. And then do you remember this condition? And you obtain immediately that the sum from I equal 1 to n of xi times pi is less than or equal to I. But this number is x times p. So in other words, x is one of those vectors that satisfy the properties in this set. And what have you done? So I'm going to summarize it. So you started off by taking a sequence in this set that converged to certain vector. And you saw that that vector belongs to this set. This proves that this set is closed. And before you showed that this set was bounded, so as a consequence, this set is compact. And so there is a solution for the problem. There exists a solution for the problem. Which one? The utility maximization problem, right? Now, what's the solution? Well, that's going to depend on the expression of the function u, right? So, but as long as u is a continuous function, there exists a solution. Okay. So this is a simple application of Weierstrass theorem to the utility maximization problem, and we are going to continue in 2 days with more applications, and we are going to check the proof of Weierstrass theorem. Do you have any questions today?
I don't have any.
No?
Yeah, I don't have either.
Okay, so
No.
so was it clear? Oh,
Yes.
okay, okay, pretty good. So you had seen this theorem before, I guess?
Yeah, we talked about it last year.
With
How,
you.
like the math programming, or what did we have? Anyways, yeah.
Yeah. That's right. So yeah, so I just wanted to remember this theorem again, and because it's important and because there are other classmates, of course.
Yeah.
But Yeah, but this is the most important tool to determine if a maximization minimization problem has a solution. All right, so we're going to give the proof, and the next stop will probably be Lagrange's theorem. Any questions?
No.
Comments? No. And Hilary and